Julie. Our next speaker is Daniel Britt, also from the University of Central Florida.
Well, welcome. So I'm going to talk about the dehydration of serpentine. Why am I interested in serpentine? Well, pardon me?
So you better be. It's all over
Yeah, it's as our esteemed co-chair says, it's all over these critical carbonaceous chondrites, particularly Bennu and Regu. And basically, when you talk about water-rich, volatile-rich asteroids, basically the water is in the form of OH, water in quotes, in the crystal structure of the serpentines. So what's going on is that serpentines are alteration products of higher temperature silicates, typically olivines. The way you get this stuff is in the early days of solar system accretion, these high temperature materials, the olivines, accreted with low temperature materials and had this soup of dust, of high temperature dust and low temperature volatiles. Things being what they were in the early solar system, that melted. This stuff is in huge chemical disequilibrium. And so when the ice melts, the silicates react, and the reaction product of your olivines is going to be serpentines. And so you take stuff that started out water and olivine, and essentially you get that, which is a soggy dirt clod. And if you don't believe that these things are soggy dirt clods, you can go to a major natural history museum, hold one in your hand, and you can easily crush it into dust because that's how strong it is. Of course, that would be a career-ending move for anyone who does that. I was tempted when I was a graduate student, but I resisted. And the amount of alteration depends upon the amount of water incorporated in the original nebula. So just to illustrate with CM carbonaceous chondrites, which might be what is the parent material of some of these asteroids we're going to, all of this circled in red are alteration products. So some of these guys are 90% alteration products. CR chondrites are highly variable, so some of them have 90% alteration products, and some of them don't, are 85% not alteration products. So you have and basically what the driver is how much water was originally incorporated and how that water reacted with the original matrix. And so the amount of water in the early solar system, and this bothers the hell out of me, is hugely variable. And I keep coming up to Bill Bodke in all these meetings, and I've seen him 3 times across 9 time zones in the last month. And I say, why is the water so variable in the solar system? And Bill is getting annoyed at me. But
that started before we started seeing it.
Yeah, that's true. That's true. But, you know, this water-rock ratio, you know, why is that? Anyway, put that aside. That's not the point of this talk. But, you know, that's one of these annoying features about the solar system is that they keep giving you hints about how the solar system originally developed, and they don't seem to fit into my mental picture. And that's my problem. As the old principle of planetary science goes, if you don't understand the data, it's not the data's fault, it's your fault. So this is just my fault. Anyway, but this is just a feature that is interesting. So if you look at the volatile-rich carbonaceous chondrites, serpentine and its various polymorphs just dominate the mineralogy. And so a quick lesson in serpentine mineralogy. Serpentine is a broad group in mineralogy. and you have magnesium-rich polymorphs. So Antigorite, lizardite, and I can't remember the next one. Pardon me? Oh, there. And then you have an iron-rich polymorph, Cronstedtite. Why we care is that probably the volatile-rich carbonaceous chondrites that get into the inner solar system are highly susceptible to spectral alteration by very modest heating. And the reason is that these serpentines are highly unstable when you start to heat them up a little bit. And the question, the question that I have, well, let's get to that in a minute. I just want to point out that these are kind of just very basic thermal processing experiments. And this was done in atmosphere, so the chemistry is completely off. But very modest heating really hammers the spectra of things like Murchison, that's a CM carbonaceous chondrite, or a Vuna. So unheated, you know, heated 100 degrees drops the albedo like 40%. Something's going on there. 300 degrees C drops it by 200%. If you irradiate it with lasers, you know, the same thing. You get spectral alteration. That is probably, you know, people talk about Benno and Ryugu being different spectral types. Probably, that really doesn't tell you anything about mineralogy. All that probably tells you about is its alteration history. It might very well be that they're the exact same stuff. So, the whole point is that serpentines are low temperature materials. They will break down with fairly modest temperatures, and that the orbital evolution of near-Earth asteroids will produce those kinds of modest temperatures. And what we want to do is look at the products that you get in this kind of alteration. When we went into this, we found out that most of the data for serpentine dehydration is actually at high pressure. And you actually don't have any data for vacuum conditions. So what we're trying to do is determine loss rates at various grain sizes, heating rates, and also vacuum versus pressurized conditions. We started out with doing the thermal gravimetric analysis. Basically, all you're doing is heating and measuring the mass and watching the mass loss while you're heating. And so this is mass loss, and this is heat flow. And so the way you interpret heat flow is that basically you're getting phase changes within the minerals when you see peaks or valleys in the heat flow. And so the bottom line here is that the pointer doesn't work all the time.
But you have to just hold it.
Yeah.
And I'll change it. I'll change it.
Okay.
You killed it.
I killed it.
There it
Well,
is.
oh, okay. It's just,
There's a delay.
yeah, there's a delay. So typically what you're doing is you basically rock solid until 550 C, and then you fall off a cliff with Antigorite. Lizardite, another polymorph, more or less the same story, about 550 C, a couple of phase changes. By 800 C, you're dropping down to mass losses in the range of 12%. What's interesting is for Cronstedtite, which is the iron-rich polymorph, the first two were magnesium-rich polymorphs. You start altering this stuff around 300 degrees C, which is not hard to obtain in the inner solar system. And then you get very rapid mass loss and big mass loss, like 20%. Out to less than, and you're basically done at 600 C. So major change. And this is what you saw in the teaser slide, the comparison between Cronstedtite and Antigorite. So basically same crystal structure. The difference is in the cation that this thing is built around, which is iron versus magnesium. Magnesium polymorphs are a lot more stable. And the thing is that what you see in the spectral classes in asteroids, particularly in the inner solar system, are probably going to be alteration products. That the broad C class of asteroids in terms of spectroscopy probably doesn't mean anything in mineralogy. That you can get the same stuff, the same spectral result with a bunch of different spectral results with the same stuff. And so the other thing is that you can do this in vacuum. And the approach here is that this is in about 10 to the minus 6th torr. But what happens is that you change the onset temperature by about 50 degrees. So it makes Cronstedtite even more susceptible in hard vacuum. So you get thermal alteration at fairly modest temperatures, even for the magnesium-rich serpentines. The iron-rich serpentines, which might be the CM carbonaceous chondrites, are dominated by Cronstedtite. And their dehydration temperatures are a lot lower than the other serpentines, 200 degrees C. Vacuum has an effect, and that decreases dehydration temperatures. You get different mass losses depending upon the crystal, the mineralogy. But the bottom line is that CM parent bodies are going to weather differently than other volatile-rich carbonaceous chondrites. And that basically you should expect that all of these dark volatile-rich asteroids in their solar system are going to be thermally altered. And they are going to, the spectra is not really a great guide to what you get, because you can have vastly different spectra and the same things. Thank you.
We have time for one question. Why don't you get the mic over here, please?
So I actually have two questions, but they're going to be quick. So one is, what's the rate of mass loss? And the second one is, so that mass loss, is it lost in the form of molecular water or OH?
The loss is in form of water and OH. So the OH does combine with whatever's around and generally makes water. The rate is actually very fast. So it is a function somewhat of particle size, because you have to communicate these things with crystal structures. Finer stuff goes faster.
We'll have a few minutes for discussion for all three of these talks.